All right. Now for the last part, before we can understand fully how vectors and centroids actually apply in engineering, although we had some hints already in the previous slides, um, we there are some physical quantities that we have to introduce. Okay. Most first of which is the inertia, which describes a system's in resistance to change in motion. Take note that whenever there's mass, there's inertia. Um, okay, let's say a heavy person, a person with a very high mass, will most likely have a higher resistance to change in motion. It will not be easy to push that person because of its mass. Uh, Also, in the same way, if a heavy person is moving, it will not be easy also to change its motion. Uh, if you try to block its way, then that obstacle must be big enough to stop. All right. Inertia is also considered to be the resistance most naturally referenced to for distributed systems to the center of mass or the COM vector. Okay, so if you're talking about inertia, then you have to understand first what is a COM or the center of mass, or for simplicity, what is the centroid for it. Okay, so here we have this formula, the RC or the effective location of the mass distribution. Just divide just multiply 1 over m to the integral of the position vector r multiplied to the differential mass. Okay. Um, the translational response of a body can be analyzed as if its entire mass were concentrated at this point. Okay. So we are considering uniform or homogeneous distribution of mass in an object. Okay. So where do we get apply this? In mobile robots, drones, and automated platforms, control stability, which is a very important property of a system, depends on accurate centroid and center of mass estimation to account for inertial effects of batteries, sensors, actuators, and different motions that may be involved in their operations. Okay. We have a funny image here, as you can see. If you can observe, sorry for them. But um, the what's actually happening here is I think it's a bus. The bus is moving very fast, okay, but it suddenly stopped. Okay, so that's what the definition was actually saying. Um, okay, if an object has a certain mass and it's moving, okay, that object is moving at a very high speed, whether it's moving itself or just riding inside the or it's inside a moving object like a bus, then it will be too difficult to stop its motion or to change its motion. Okay, so since we have like us when we ride a fast moving car or any vehicle, okay, whenever the vehicle stops, we tend to move that way. Okay, because we have the tendency to continue our motion. Okay, there's and that tendency is due to our inertia. Okay, so the higher the mass, the bigger or the harder it is to stop that motion, stop or change that motion. Okay, so that's why we have seat belts. Yeah, like whenever you see seat belts, just remember, oh, that's inertia. Okay, another illustration of inertia is what we call gyroscope. Okay, so first, simple illustration of a gyroscope is a bicycle wheel, like what you see in the image. So try to spin the bicycle wheel very fast. Okay. But before that, sit on a rotating chair. Okay. Sit on a rotating chair like what I have right now. So try to spin the bicycle very fast and then um let it spin and then um just avoid your feet to stay on the floor, right? Or to get to be in contact on the floor and then let the chair rotate. Right? You will find that uh depending on your orientation of the wheel, there will be motion. There will be a responding motion to your rotating chair. I like what you see in the animation. Okay, so whenever you see that, okay, you can say, oh, that's inertia, right? Um, Another thing, because of inertia, it's not easy to reverse a certain direction. Like if an object is moving clockwise, then uh it will resist whenever there's a change in motion. It will resist to move the other way. Okay, that's also something that we consider whenever we have components like motors in our system. Okay. Um, Next, note that when a force does not act through the centroid, it produces a moment. So this is another important concept, especially in engineering applications. So moment, it's at the moment with your loved one or whoever. Moment, and sometimes it is as closely associated with torque. Okay, so we're going to have more formal discussions on these concepts once we go to the next module. Okay, so right now we are just introducing these terms. Um, Again, when a force does not act through the centroid, then there will be a moment. Okay, like this, like what we have in our animation. Okay, so there will be a moment or the tendency to have a rotational motion. Okay. Moments arise purely from the vector offset between force application and the centroid. Okay. So we have the formal definition of torque and moment right away. By the way, let's read this. So torque is a movement force and it is often presented as Newton meter per revolution. Newton meter, Newton times meter divided by the revolution. And torque tends to be used when there is an axle or pivot to be turned around, like what we have with our what do you call this? That wrench or screwdriver or in our levers or in our hinges, right? So just like this one, okay? So whenever there are these things and they are meant to be rotated, then we can say there's torque. Okay. On the other hand, we have moment, which is a static force, and it is typically presented as Newton meter. Okay, so as you can see, torque is basically moment per revolution. Okay, so moment tends to be used in essentially non-rotational situations, such as analysis of forces on a beam. So usually we are concerned on moments when the objects are not supposed to rotate. Okay, while we are concerned with torque when the objects are supposed to rotate. Okay, so I guess that's the simplest um distinction or contrast between the two terminologies or physical concepts. Okay. Note also that using centroidal axis simplifies moment calculations, separates translational and rotational effects, and improves symmetry in design and analysis. And we're going to talk more about these things in the next module, actually. Okay. Balanced systems, those are very important concerns in the next module, have minimal unintended torque. Okay, remember when an object is supposed to stay on its designated position, then there should be no unintended torque when forces act through centroidal points. Right? So, okay, because our structures like buildings and bridges are not supposed to move. Okay? So they should have no any untended, or they must not be subject to torque unless the building is supposed to rotate. Right? Anyway, well, inertia describes resistance to linear motion. The moment of inertia quantifies the resistance to rotational motion. Okay. Remember we have the term inertia earlier. And whenever we are now concerned of rotational motion, then any object has a tendency to resist that rotational motion. And it depends on the geometry of that uh, object as well as on its material, right? But for now, our focus is more on the geometry. Okay, observe, before we talk more about that, observe these objects being rolled down in an inclined plane. Okay? Observe, they have different shapes, but observe how they move down through the plane. Okay? All right. So geometry matters, and that's why when designing vehicles or any mobile objects, uh, we make sure that we are using the right geometry in the different parts of our system, because they affect how the overall system moves through the environment. Okay, and that is basically based on the moment of inertia. um Moment of inertia depends not only on the total mass of a body, but also on how that mass is distributed relative to a chosen axis, which is often a centroidal axis. Mass farther from the centroid contributes more strongly to rotational inertia. Again, mass farther from the centroid. So, for example, there's a centroid and you have this much mass away from it, then they have more. If a force is exerted on that part, on the heavy part, then there will be a bigger chance that the object will rotate. Okay, so um for discrete systems, we have this formula for solving the moment of inertia. Basically, we just sum the take the sum of the individual moments and their respective perpendicular distance from the axis of rotation. Okay, squared of those r. And for continuous systems, we use this formula. Uh, for discrete, we use summation, but for continuous, we use integration. Right? Where r is the perpendicular distance from the axis of rotation, and dm is the differential mass of that object or element. Okay? And you as you can see here, depending on the moment of inertia of an object, the we can determine how fast that object will rotate with a given applied force. Okay? So kindly observe. Right. And lastly, we have the concept of equilibrium. So before we study the statics and dynamics of a rigid body, we have to understand what equilibrium is all about. So it's basically a state where an object experiences zero net force and zero net torque, resulting in no change in its motion, characterized by balanced forces and moments. So we can only achieve equilibrium or the stability of an object when it comes to space when the forces and the moments are balanced. Okay, meaning it does not move um in any of the axis, x axis, y axis, z axis, and it does not rotate in any plane. Okay, in XY plane and YZ plane, or in what's the other one? XZ plane, right? We have a more specific uh type of equilibrium. Okay, or should we say we can further distinguish equilibrium as either static or dynamic. When we say static, the object is at rest. Okay, meaning there's no motion, no acceleration. But when we say dynamic equilibrium, the object is moving but at a constant velocity. Okay, so there is still no acceleration. Remember, if okay, we're going to talk about that in module 4, but um for now, just remember that if there's constant velocity, then there's no acceleration. Okay? Because if you can still remember, acceleration is our um the change in velocity with respect to time. Okay? So, and here, note, in summary, note that a system is said to be in equilibrium when there is, number one, no tendency for translation, meaning the summation of all the forces is equals to zero. No, no, what do you call that? No, um, no X resultant. Okay, the resultant, wrong. Um, the sum of all the X components of the forces is zero. The sum of all the Y components is zero. And the sum of all the Z components is also zero. Okay. So that when that happens, then the summation of your force, or meaning the resulting summation of the forces, will be equal to zero. So uh it's not easy. Okay. X, Y, and Z must be zero. Okay. And when it comes, same thing when it comes to rotation. So, system is said to be in equilibrium when there is no net tendency for rotation for along x-axis, along y-axis, and along z-axis. Okay. And usually we are analyzing whether a system is in equilibrium or not with the help of a free body diagram, or FBD. So it is a simplified graphical and mathematical model that isolates a body or a subsystem, and it represents all vectors or all external forces as vectors, and references forces and moments to centroidal or chosen coordinate axis. Okay, and that ends our module. And actually, this is the turning point. This is the part where we uh up, uh, okay, we integrate these different concepts of vectors and centroids, and apply them into the statics and dynamics of rigid bodies. Okay, we are in the next module. We're going to analyze first the statics of rigid bodies. Okay, and these concepts are all important, right? So I hope we're clear with the some of the concepts. If not yet clear, then maybe our handouts where we have our sample problems can help. Or maybe we can discuss them in our face-to-face meetings. Okay? So that's it for our module 2. Okay, bye-bye. See you in our next module.